Hello everyone and welcome to the Pneumatic controller for our cardiovascular flow loop. Our team of 5 engineering students is helping Dr. Kaloji with this project. Currently, the main problem that we're facing is that the old system is at risk of breaking due to its age and cannot create the proper waveforms for a heartbeat.
Similar to the heart, blood enters the ventricle due to lower pressure and is ejected through muscle contractions. This can be simulated with a silicone sac that compresses and ejects fluid into the flow loop. Modeling the heart in this way can help study LVADs or pacemakers under different simulated heart conditions to improve efficacy. We were asked to create a pneumatic controller that took user-controlled input signals to pressurize and depressurize the ventricle bench at a desired ventricular contraction in order to accurately represent the Wiggers diagram pressure waveform. We wanted a simpler, smaller, quiet, and more stable system.
Our final concept consists of a linear actuator and cylinder. The linear actuator is programmed with position and time points in order to move the piston and pressurize the ventricle. This pressure is then recorded and outputted to represent the ventricular pressure seen in the Wiggers diagram. By moving the piston, we compress a constant amount of air into a smaller volume. At a constant temperature, we can pressurize the system according to the simplified ideal gas law of PV equals PV, where the total pressure and volume are equal at different states. The same is done by decompressing the air and depressurizing the system.
Putting our idea into action was certainly a journey. We ran into many different issues, from getting a hold of IT, to base plate movement and misalignment due to oscillations in the sheet metal, to air leakage and fitting issues. After fixing all of those problems, we were able to see our idea in action and finally get results.
Programming was a major part of this project. Our goal was to create a sine wave that was similar to the pressure waveform on the Wiggers diagram. This took many different methods, from mapping out all the points first, then running it through, using trial and error to weed out any of the unwanted bumps, until we consistently got a waveform we wanted. In the future, more work will need to be done to the system or the programming in order for it to match the Wiggers diagram more closely. But as for now, we are confident in its ability to get a sine waveform that is similar to that of the Wiggers diagram.